Okay, good morning again. This is the third video, and in this video we are going to solve some problems on the application of moment of inertia and parallel axis theorem. So if you want to again just go over the second video, you will know all the formulae that we need in order to solve or in order to apply parallel axis theorem and basic formulae for standard shapes or basic formulae of moment of inertia for standard shapes. So here we are going to solve maybe 2 or 3 problems. Let's see how it goes. So let's start with example 1. The problem asks us, problem says that we have a beam which is made up of T section. Okay, let me draw this into proportion. So we have a beam which is made up of T section, and the dimensions are 10 millimeter. This height is 30 millimeter. Again, this top area is 10 millimeter, and total width is 40 millimeter. If you remember from video 1, the example of centroid that we solved is exactly similar to this, but we just had an inverted T in that case. So I've chosen the dimensions to just save some time. So the question is, find moment of inertia of this T cross section about the neutral axis, because we know that bending stress for a beam is given by MC over INA, where INA denotes moment of inertia about the neutral axis. Now, in case of beams, neutral axis, we know that neutral axis always passes through the centroid of the cross section. So in order to find moment of inertia about neutral axis, a very important step is to first locate the centroid of this T section. If you remember from first video, T section is symmetric about y-axis, vertical line, and if you actually go back and look the first video where we determined the location of centroid of this T section lies at a distance of 13.75 mm from this surface here. Okay. And we are going to start our problem for finding moment of inertia from this point about the neutral axis, which is nothing but the centroidal axis. So we identified 2 shapes here, upper rectangle and lower rectangle. Now we know that in order to find moment of inertia of this rectangle, which has this centroidal axis, and the smaller rectangle which has its own centroid located somewhere here. So the procedure or the conventional way of solving this problem would be to find moment of inertia of this upper rectangle about its own centroidal axis, which is here, and then using parallel axis theorem transfer that moment of inertia from this axis to neutral axis, and then add moment of inertia of this rectangle about its own centroidal axis and then transfer it again to the neutral axis. So if you try to solve this problem using conventional method, we basically have to apply moment of inertia 2 times. So to save some time, we are going to apply, or we are going to use an alternative way in order to solve for moment of inertia about neutral axis. For that, we are going to identify, let me just erase this common, or these 2 centroidal axes of the individual areas. Okay. Okay, so it looks pretty clean now. So in order to use alternative method, we identify an edge or an axis which is common to both of the rectangles. So this rectangle and this rectangle share this edge here. And since these are rectangular shapes, which are standard, one of the standard shapes, we know that for a rectangle, moment of inertia about one of its base is, I'm going to write it to be common edge, which is this edge, is given by ph cube over 3. If you don't know this formula, this is given in the textbook because this is a standard shape, this is standard formula for moment of inertia of a rectangle about its base. So the way we are going to find, or we are going to approach this problem is, we are going to find moment of inertia of this rectangle about common edge. We are going to find moment of inertia of this lower rectangle about this common edge, and add those two together, and then apply parallel axis theorem just once to transfer moment of inertia from common edge to the neutral axis. Okay, so let's start. I common 1 is moment of inertia of the upper rectangle, let's denote this by 1, about its base, which is bh cube over 3. The breadth is 40, the height is 10. So 40 into 10, sorry, 40 into, it is 40 into 10 cube over 3. This gives you, I don't know the number, but I think it is 13.33. 13.33 into 10 to the power 3. Remember, we are dealing with, let me write, all dimensions in millimeter, and unit of moment of inertia is millimeter to the 4th. So this is moment of inertia of this top rectangle about the common axis. Similarly, moment of inertia of the lower rectangle, which is denoted by 2, is again bh cube over 3, and this will be 10 into 30. So 10 into 30 cube over 3, and if you solve this, I think it comes out to be somewhere around 90,000. Yep. So 90 into 10 to the power 3, again millimeter to the 4th. Okay, so this one and this one, ICOM 1 and ICOM 2, are moments of inertia of these two rectangles about a common axis. So what we are going to do now is, we are going to write ICOM is equal to ICOM 1 plus ICOM 2, and we are going to put the numbers here, which is 13.33 into 10 to the power 3 plus 90 into 10 to the power 3. So we are going to add moment of inertia of ICOM 1 and ICOM 2, which are moments of inertia of these two rectangles. If we do so, we get ICOM, which is moment of inertia of this entire composite area or entire T section, and this number becomes 90 plus 13 is 103.33 into 10 to the power 3. So the units are millimeter 4th. So what we have done is, we have found moment of inertia about the common axis of the entire T section. But in order to apply the formula for bending stress, which is mc over I, we need to find moment of inertia about the neutral axis. We know moment of inertia about common axis, we want to transfer it from this axis to the neutral axis, and for that we are going to use parallel axis theorem. Okay, so we want to find moment of inertia about the neutral axis, which is essentially the centroidal axis. If you go, oh okay, I erased it there, but we know that moment of inertia about the centroidal axis is always smaller, so we have to subtract the term a d square. So this is something that we discussed in the previous video. If you are confused with the notations, then I think this was Ix, which is centroidal axis, is equal to Ix prime, which is an axis which is not the centroidal axis, and A into d square. Okay? So we know I common here, which is 103.33. So let's plug the values in it, which is 103.33 into 10 to the power 3 minus A, which is area of this P section, okay, which is 400 into 40 into 10, which is 400, area of the top rectangle, plus 30 into 10, which is 300. So 400 plus 300. So the total area is 700 into d square. The d square, as I mentioned earlier, d is the transfer term, which is basically the distance between the two parallel axes. We are considering neutral axis and this common edge here, and from this point here, this is 13, and from the same point, this is 10. So this distance is basically 3.75 millimeter, the distance between the two parallel axes. So we are going to substitute it here, 3.75 square. Okay, now, I mean, the problem is basically solved now. If you do this calculation, you will get a number which is 94.755. 94.755. We have too many significant figures. We don't need this one. Millimeter to the power of 4th. So this is the answer you are looking for. We wanted to find moment of inertia about the neutral axis, because we want to substitute that in here to find stresses on the cross section of the beam. And one of the again important things that you should remember is moment of inertia about neutral axis is the smallest. See, 94.75 is less than 103.33. So we are correctly applying the parallel axis theorem. Okay, so this is end of problem 1, and now we are going to discuss second problem, which is here. No, that is so. So second problem. The problem says that we have, okay, we have a box beam which is made up of 4 different wooden parts. So 1, this horizontal, 2nd, 3rd, and 4th. And these 4 wooden bars or platens are glued together. So this is glue, this is glue, this is glued, and we have 4 glue joints. And just to put the dimensions in, let's say this is 1 feet, this is 2 feet, this is again 1 feet, and to make the calculation simple, say this is again 1 feet, this is 2, and this is 1 feet. Let me just cross check the numbers here. Okay, perfect. So again, the problem is same. Find moment of inertia of this box beam about its neutral axis. And again, all dimensions are in feet. Okay. So If we want to solve this problem using the method that we described in problem 1, we should note that in order to solve this problem using by using method similar to first problem, we'll need a common edge, but here there are 4 different parts and we cannot use, or we do not have any common edge. So what we'll have to do is we have to use parallel axis theorem for all of these individual parts. So we'll have to use parallel axis theorem 4 times, and which will be like pretty time consuming. So here I'm going to show you another approach on how to solve problems when we have a beam made up of a box section. So in order to explain this, let's first locate the neutral axis, and we know that this box section is symmetric about both y-axis and x-axis. So we can very easily locate the center of this box beam. So again, the centroidal axis is nothing but the neutral axis for a beam cross section. Now what we are going to do here is we are going to replace this box beam. You can see that there is wooden parts in this shaded region here. And this is hollow. There is no material in here. So what we are going to do is we are going to draw an, let me first set up the problem correctly. So this is the neutral axis extended towards right. We are going to draw an outer rectangle, okay, which is 4 feet wide and 4 feet high, which is nothing but 1 plus 2 plus 1 is 4. It's 4 here. 1 plus 2 plus 1 is 4, which is 4 here. This looks like a rectangle, but remember this is 4 by 4, so it should be a square, but it's okay. And we are going to draw this small rectangle here, which is, or small square, which is 2 and 2 here. So so this is 2. This is also 2. So what we are going to do is we are going to fill this rectangle completely with wood 4 by 4, and we are going to subtract this hollow portion, which is small square of 2 by 2 dimensions. So we can clearly see that a solid rectangular or square cross section completely filled with wood, and then we are going to take this part out, which is 2 by 2 mm, which represents this hole. Clearly, since both of these are symmetric, we know that this is going to be the location of neutral axis for both of them, which is essentially same as this neutral axis. And we are going to use, let's call this solid, and this is, let's call this hole, or no, let's call this hollow. Okay? So in order to find, or in order to solve the original problem, which is to find moment of inertia of this beam with 4 wooden plates or 4 wooden parts and hole in the center, let's denote this by ORG, which corresponds to original cross section, and this is given by I of solid minus I hollow. Okay? Find the moment of inertia of the center solid area and then subtract moment of inertia of this hole, because in actual beam cross section we don't have any material in the center. So this becomes very simple problem now. A moment of inertia of a rectangle about its own centroidal axis is given by, let me write I for rectangle about its centroid is bh cube over 12. So if you apply this formula into these two expressions here, I solid is going to be b, which is 4, into h cube, which is height cube, 4 cube over 12, minus I of hollow square, which is b is 2 and height is also 2. So minus 2 into 2 cube over 12. Okay, so if you solve this, 4 into 4 into 4 is, I guess, 256 over 12, minus 2 into 2, 4, 4 into 4 is 16 over 12. Okay, I may be wrong in calculation, but I'll get this number correct, and that comes out to be 20 feet to the power 4. So this is the final answer. 20 feet to the 4 is the moment of inertia of our original cross section, which was a box beam with a kind of hole in the center. So this is an example of a box beam. Let me give you another example where you can apply this method of subtracting moments of inertia of solid and hollow portion, and that example is, let me erase this. That example is an I-beam, which is also very commonly used cross section for the beams. So this is an I-beam, so obviously it is symmetric about both x and y axis, and this is the location of centroid. So again, you can see there are 4 different parts if you consider this as a composite area. 3 different parts, 1, 2, and 3. So rather than using parallel axis theorem 3 times, what you can do is you can replace this with a rectangle, which is, let's say, b by h. So this is b and height is h. Okay, so this is the solid portion, and we are going to take off these 2 small rectangles. Okay, so let me just highlight them here. So if you take these 2 rectangles out, you will get your original beam. So this solid minus a rectangle here and another rectangle here. And again, the neutral axis passes through the line of symmetry. Let me just erase this thing. So again, you can treat this as a solid and then subtract 2 moments of inertia of these 2 small portions here, small rectangles. So you can call them hollow. So this is another example where you can easily solve for the moment of inertia of I section by subtracting I solid into I hollow. But remember, this I hollow will be consisting of moment of inertia of both of these rectangles. Okay. Similarly, just if you go back to the other board here, where we had a T section, we made use of a common edge in order to find moment of inertia for this T section. You can also solve a problem of an angle section like this, where you can use this edge as a common edge, or it can be even other shape like this. Okay, or if you want to go one more step, then if your cross section is U cross section, then you can see that this is a common edge here, and all of these problems can be solved with the same method that we used to solve example 1. And from these 2 examples, you can solve most of the common problems on finding moment of inertia of composite area about the neutral axis. Okay, so this finishes segment 3 on examples of moment of inertia and application of parallel axis theorem. Thank you.